Canny College is dedicated to empowering individuals to excel in their HVAC mechanic trade through top-notch preparation courses for the HVAC mechanic licensing exam. Our online course is comprehensive and designed to equip you with the skills, knowledge, and confidence needed to pass the demanding Red Seal trade license exam and earn your refrigeration and air conditioning mechanic certificate of qualification. We are your trusted pathway to success in the Canadian Red Seal Trades license exams, a crucial milestone on your journey to a rewarding career in the skilled trades industry. Aspiring professionals seeking a Canadian Red Seal trade license can rely on our institution's expertise. Canny College offers comprehensive online exam preparation courses for various skilled trades. It uses an innovative learning approach and a commitment to excellence to equip students with the essential skills and expertise required to succeed in their chosen trades. Visit our website at www.cannycollege.com for more details. Please note that the practice questions provided here demonstrate the structure and phrasing of Red Seal examination questions. They are for study purposes only and do not result in certification or reflect actual performance on the examination. Question 1. Given the following information: parallel compressor system. Compressors are cycling on low-pressure controls. The receiver liquid gauge is showing an empty. The sight glass is flashing. Head pressure is low. What is the cause? A. Reed valves are faulty. B. Split condenser valve is leaking. C. The discharge differential valve is leaking. D. The oil pressure differential valve is stuck open. The correct answer is B. The split condenser valve is leaking. Here are 4 reasons. 1. In a parallel compressor system, the split condenser valve plays a crucial role in regulating the flow of refrigerant and maintaining proper system operation. If the split condenser valve is leaking, it can result in a loss of refrigerant from the system, leading to issues such as low head pressure and insufficient refrigerant circulation. 2. The fact that the compressors are cycling on low-pressure controls indicates that the system is not maintaining the desired pressure levels, which can be a result of refrigerant loss due to a leaking split condenser valve. 3. An empty receiver liquid gauge and flashing sight glass further suggest a shortage of refrigerant in the system. A leaking split condenser valve can contribute to the depletion of refrigerant in the receiver and hinder the proper refrigerant flow necessary for system functionality. 4. The combination of low head pressure, cycling compressors, and low refrigerant indicators align with the symptoms of a leaking split condenser valve. Addressing and resolving the issue with the split condenser valve can help restore the refrigerant balance and optimal operation of the parallel compressor system. Question 2. Why are glycol inhibitors added to chilled water loops? A. To prevent corrosion. B. To prevent ruptured piping. C. To increase heat exchange. E. To decrease bacterial growth. The correct answer is A. To prevent corrosion. Here are 4 reasons. 1. Glycol inhibitors are added to chilled water loops to prevent corrosion of the system components, such as pipes, fittings, and heat exchangers. Corrosion can lead to equipment damage, leaks, and reduced system efficiency, making it essential to use inhibitors to protect the system. 2. The presence of glycol inhibitors forms a protective layer on the metal surfaces within the chilled water loop, inhibiting the formation of rust and other corrosion-related issues. This protective barrier helps extend the lifespan of the system components and ensures their proper functioning. 3. Corrosion in chilled water loops can lead to the formation of scale deposits, reduced heat transfer efficiency, and increased energy consumption. By using glycol inhibitors to prevent corrosion, the system's overall performance and energy efficiency are maintained, resulting in cost savings and improved system reliability. 4. In addition to corrosion protection, glycol inhibitors also help prevent freezing in chilled water systems when used in the appropriate concentrations. This anti-freeze property is especially important in regions where low winter temperatures pose a risk of freezing the water in the system, which can cause damage to components and disrupt system operation. Question 3. The crankcase on a semi-hermetic compressor is very hot. What is the cause? A. TXV, TV, spring is broken. B. Piston rings are defective. C. Oil separator float is seized closed. D. Liquid line solenoid valve coil is inoperative. The correct answer is B. Piston rings are defective. Here are 4 reasons. 1. The crankcase being very hot in a semi-hermetic compressor can be indicative of defective piston rings. The piston rings help seal the compression chamber, ensuring proper compression and preventing excessive refrigerant leakage into the crankcase. 2. Defective piston rings can lead to poor sealing, causing the refrigerant to bypass the rings and flow into the crankcase. This can result in increased pressure and temperature within the crankcase, leading to the observed high temperatures. 3. The excessive heat in the crankcase due to defective piston rings can impact the performance and efficiency of the compressor. The increased temperature can also affect the oil quality, potentially leading to oil breakdown and lubrication issues. 4. Addressing the defective piston rings is essential to resolve the issue of the hot crankcase in the semi-hermetic compressor. Replacing the piston rings will help restore the proper sealing of the compression chamber, prevent refrigerant leakage, and reduce the crankcase temperature to ensure the compressor operates efficiently. Question 4. A TXV (TV) power element capillary tube is cracked. What is the result? A. High suction pressure. B. Low evaporator superheat. C. High compressor superheat. D. Low compressor discharge temperature? The correct answer is C. High compressor superheat. Here are 4 reasons. 1. When the power element capillary tube of a TXV TEV is cracked, it can result in an inaccurate sensing of the refrigerant temperature at the evaporator outlet. This can lead to improper modulation of the valve, causing inadequate refrigerant flow to the evaporator coil. 2. Insufficient refrigerant flow due to a cracked power element capillary tube can result in high compressor superheat. High compressor superheat means that the refrigerant vapor leaving the evaporator coil is excessively heated before reaching the compressor, affecting compressor efficiency and operation. 3. High compressor superheat can lead to increased compressor workload and potential overheating, reducing the overall performance and lifespan of the compressor. It can also impact the system's cooling capacity and efficiency, resulting in poor cooling performance and higher energy consumption. 4. Addressing the issue of a cracked power element capillary tube is essential to ensure proper refrigerant flow and system operation. By repairing or replacing the damaged capillary tube, the accurate regulation of refrigerant flow to the evaporator coil can be restored, helping to maintain optimal system performance and efficiency. Question 5. The RPM of a ducted fan moving 200 CFM is increased. What is the result? A. Fan motor amperage increases and total external static pressure increases. B. Fan motor amperage increases and total external static pressure decreases. C. Fan motor amperage decreases and total external static pressure increases. D. Fan motor amperage decreases and total external static pressure decreases. The correct answer is A. Fan motor amperage increases and total external static pressure increases. Here are 4 reasons. 1. When the RPM of a ducted fan is increased, the fan motor amperage typically increases as well. The higher RPM requires more power to drive the fan at a faster speed, leading to an increase in the motor amperage. 2. Total external static pressure also increases when the fan RPM is raised. As the fan speed increases, it generates more airflow, which can lead to higher air resistance and static pressure within the ductwork and system. This increased resistance contributes to the rise in total external static pressure. 3. The relationship between fan speed, motor amperage, and total external static pressure is interconnected. Increasing the fan RPM impacts both the power consumption of the motor, amperage, and the system's ability to overcome resistance, external static pressure. 4. Understanding the consequences of adjusting fan speed is crucial in HVAC systems, as it can impact the system's performance, efficiency, and energy consumption. Monitoring variables such as motor amperage and total external static pressure helps HVAC professionals optimize system operation and troubleshoot issues effectively. Question 6. Which type of refrigerant requires the allowance of glide when calculating superheat? A. Zeotrope. B. Azeotrope. C. Near zeotrope. D. Near azeotrope. The correct answer is A. Zeotrope. Here are 4 reasons. 1. Zeotrope refrigerants are comprised of multiple components that have different boiling points and vapor compositions. This results in a temperature glide, where the refrigerant blend does not evaporate or condense at a constant temperature. When calculating superheat for a zeotrope refrigerant, it is essential to account for this temperature glide. 2. Azeotrope refrigerants, on the other hand, behave as a single component with a constant boiling point and vapor composition. There is no temperature glide in azeotrope refrigerants, so calculating superheat for these refrigerants does not require the allowance of glide. 3. Near-azeotrope refrigerants have a small temperature glide, but it is typically negligible. In most cases, the glide is minimal enough that it does not significantly impact superheat calculations compared to zeotrope refrigerants. 4. Near-zeotrope refrigerants have a moderate temperature glide, but it is not as pronounced as in zeotrope refrigerants. When calculating superheat for near-zeotrope refrigerants, it may be necessary to consider a small allowance for glide, although not to the same extent as with zeotrope refrigerants. Question 7. The valves have failed on a compressor. What is done? A. Replace the head gasket and valve plate. B. Replace valve plate, gasket, and head plate. C. Replace valve plate, gasket, head gasket, and head plate. D. Replace the valve plate, gasket, head gasket, and valve plate. The correct answer is D. Replace the valve plate, gasket, head gasket, and valve plate. Here are 4 reasons. 1. When the valves on a compressor have failed, it is typically necessary to replace the valve plate, head gasket, and valve plate gasket to ensure proper functioning of the compressor. 2. The valve plate contains the valves that regulate the flow of refrigerant in and out of the cylinders. If the valves are faulty, replacing the valve plate is essential to restore the proper sealing and operation of the compressor. 3. The valve plate gasket provides a seal between the valve plate and the cylinder head. Ensuring that the gasket is in good condition and properly aligned is crucial to prevent leaks and maintain optimal compression within the compressor. 4. The head gasket seals the connection between the cylinder head and the compressor body. A defective head gasket can lead to refrigerant leaks, loss of compression, and inefficiencies in the compressor operation. Replacing the head gasket along with the valve plate and valve plate gasket is necessary to address the valve failure and ensure the compressor functions correctly.